Okay, this is thermochemistry video notes number 2, picking up where we left off from the last time. And so now we're going to look a little bit at one of the aspects. Remember, we talked about there were 2 different aspects of energy. You have versus the work and the heat. So just a little bit here on work. Usually in an open container, the only work that is done is by the gas that is pushing on the surroundings. So you know that due to pressure, gas is going to be pushing on the walls of the container. Or another example, if you have a piston involved, then you could also have the surroundings pushing on the gas, as you would in this picture you see here adjust the position of that piston. Okay, so we can measure the work that is being done by the gas if the reaction is done in that vessel that's fitted with the piston. And so you can see that the work that's being done is going to be related to both the pressure and the volume of the gas. And so whenever a process is occurring at a constant pressure, as most of the cases that we're going to discuss in this class, that would be the way that it does work. The only work that is done is the work that is attributed to the fact that the volume and the pressure are changing. And so in order to do that, we can account for the heat flow of that process by measuring something that's called the enthalpy. So we get the enthalpy is called the internal energy. So here's the equation for enthalpy. So enthalpy, you see there, is abbreviated with a capital H. And so that is the internal energy, the delta E, which is what we saw in the last set of notes, the Q plus the W. And then we add to that the product of the pressure and the changing volume. So, like we said, since we know that the delta E, the internal energy, is Q plus W, and we know that the work is equal to the pressure and the changes in the pressure and the volume, then we can substitute those into the equation. And basically you see that if the volume, or that if the work is constant, okay, then it drops out. And the work would be constant if the volume is not changing. So if we're doing this inside of something like a bomb calorimeter, we saw that the other day, that obviously the volume of the chamber, it's inside of this big steel container, the volume of that chamber is constant. And so whenever that occurs, no work is done. And so the enthalpy is actually equal to the Q, or the heat that's being exchanged. Okay, so at a constant pressure, the change in the enthalpy is equal to the heat gained or lost. So this allows us then to kind of make a statement in terms of endothermic and exothermic that relates to the enthalpy. So the process is endothermic. Remember, that means that heat is moving from the surroundings into the system. That would give you a positive enthalpy, or a positive delta H. And if the process is exothermic, that means heat is moving from the system out into the surroundings, then that delta H, the enthalpy, is going to be a negative value. Okay, so the enthalpy for an entire reaction then is the enthalpy of the products minus the enthalpy of the reactants. So here you see a basic combustion reaction. You have methane combining with oxygen gas to produce carbon dioxide and water. And so you can see if you take the enthalpy of the products, the carbon dioxide and the water, and subtract that from the enthalpy of the reactants, that is how you can calculate the delta H. Notice here that you can see that those two values, conservation of energy. The amount of energy lost by the reactants equals the amount of energy gained by the products. And so that delta H value is called the enthalpy of the reaction, or sometimes we will refer to it as the heat of the reaction. So finally, just some few comments about enthalpy. Enthalpy is an extensive property, okay? So that means it depends on the amount of the substance that you have. So the more substance that you have, the more mass you have, the more enthalpy that a substance is going to have. Also, if you know the enthalpy for a reaction in the forward direction, You can find the enthalpy for the reaction in the opposite direction, in the reverse direction. It's simply going to be the same number, but you change the sign. So for example, if a reaction has a positive 250 kilojoules of enthalpy in the forward direction, it's going to be a negative 250 kilojoules in the reverse direction. And then finally, the delta H, the enthalpy for a reaction depends on the state of the products and the state of the reactants. So you have to look at whether we're talking about solids, liquids, or gases to know how the enthalpy is going to be affected. So for example, if you have an ice cube, and if the ice cube is melting, okay, so in this case, the water that makes up the ice cube, that's going to be your system. And so in order for the ice cube to melt, it's going to have to absorb heat from the surroundings. So in that case, delta H is going to be positive, and you're going to have an endothermic process. Okay, let's say that something is burning. Okay, let's say we have like methane burning. In that case, the methane and the oxygen that's going to be required in order to combust it, that is the system. And so as it burns, the oxygen and the burning methane are going to be giving off heat, and that heat is going to be going into the surroundings. So in that case, the enthalpy, the delta H, would be negative, and the process is going to be an exothermic one.